spectroscopic transitions and selection rules. Again, hydrogenic atoms, which are what, Pablo? What's a hydrogenic atom?
Pablo wasn't here. Were you?
No, I wasn't here Friday.
You should have watched our little.
I did.
I
just watched the.
I don't know if I posted it though.
No, you did.
Okay.
I just watched the homework part.
Pablo,
All right.
think about it. What does hydrogen have that other ones don't have?
They do have, but
What's
not as many.
About it? What's special about hydrogen?
It's
What
ground state, one proton, one electron.
Well, yeah, just one electron's key. Hydrogenic is one electron. Okay. So you can have a transition, right, from one state to another. The energy is quantized. Okay. But how do we describe the states? What do we use, Richie? What do we use to describe the states? You have these different states of these electrons. Start with a Q. There's a set of them. Quantum numbers, right? And you can have these different states described by quantum numbers, and if it goes from one state to another, and it could be either allowed or forbidden, and that's what gives rise to these selection rules. And it's really the conservation of angular momentum, right? Maybe you've heard of, in general physics, you probably did the exercises where you have two objects on a frictionless surface and they're approaching one another and they collide. You know, what's the speed of these objects afterwards? You use the conservation of what momentum to figure those out? Do you remember this? Right, especially if they stuck together, then you have to add their masses. That's momentum, conservation of linear momentum. So angular momentum is, I think it's really abstract and it's tough to imagine because we don't deal with it. You deal with it when you're riding a bike, but you don't think of it. Remember the wheel? It keeps its position in space. That's angular momentum. Okay, so there's our selection rules for hydrogenic atoms for allowed transitions. And then that gives rise to, like in figure 1319, these diagrams. And so remember, we've kind of gone full circle now. We started out with an equation that tried to you played around with these guys. High school, I think a couple high school teachers figured out a lot of these, and they said that here's a little descriptor that will give rise to all the different lines in the hydrogen spectrum, right? All the different wave numbers. You just play with these, just plug in a 1 or a 2 or a 3. So it's just kind of more like a little puzzle. But now there's actually some theory behind it, right? Where you have, they diagram out all the lines and all the Balmer series, the Paschen series, all that kind of stuff. So they have it explained through the selection rules. I don't have this in there. And you don't have your book, but unless you do. I'm looking way over in the book on page 345, equation 5, okay? And they have this equation, V is negative ZE squared all over. Now I think what we did, we had a concept preview question, I believe. I don't remember this quite well. But we had V as on top. We had the same denominator, but in physics they use Q1 and Q2. What was this equation for? What was that equation for? What are the Q's?
Electron charge.
Charges, yeah. Charge Q1 and charge Q2. And then you had the R was the distance where? Between what?
The radius is
The distance between the two, what do you call them? You don't know if they're electrons, charges, right? The distance between the two charges. So V was probably kinetic energy or potential energy? Ricky, which one?
V?
Yeah. Why would it just be potential? You're right.
Because you're looking at a stationary electron set versus.
No, they may not be electrons. You call them, they're charges, right? Q1 and Q2 are charges. They're stationary charges. Yeah.
I'm just thinking it's the energy between the atoms, not
The charges.
the charges, not moving charges or the energy that you derive from the movement of the charges.
Yeah.
But just the energy stored between
Fixed in
stationary charges.
exactly. Very good. Fixed in space, stationary. All those words fit great because R is just a fixed distance between them. So could V be positive or negative?
Positive.
Well, remember the convention. Positive if both charges are what?
Or going in the same direction?
Negative.
There's no direction for charge.
Oh.
If both charges are what? Negative? Then the charges would what? Repel or attract? Repel. That's their convention for positive. So they don't have to both be negative. They could both be positive. Would that give positive potential energy?
Yeah.
Yeah. So this is potential energy, and that was their convention. So how do you get negative? Can you get negative potential energy in that equation? What was their convention for that? They attract. So how could they attract? One's positive, one's negative. Yeah. So you get negative potential energies. You get the potential energy wells. Okay. So if you're a hydrogenic atom, in our Schrödinger equation, right? And that Hamiltonian, he had potential energy in him. This is the potential energy they're going to use. Except we're talking about hydrogenic atoms, so this expression gets turned into this.
I'm sorry, we said that the V is negative if the charges attract, right? And the V is positive
Mm-hmm.
if they repel each other,
Mm-hmm.
right? Okay.
So how do they go from the Q's to the ZE squared for hydrogenic atoms? Right, what are the two charges they're talking about for a hydrogenic atom? What would Q1 and Q2 be? Well, one of them has to be. One of them has to be it's hydrogenic. If you say proton, that means it has to be what element you're talking about? Hydrogen. Well, it's hydrogenic, so it's not hydrogen. It could be any element, but it has to be hydrogenic. So one of those charges has to be what? What's the idea of hydrogenic again?
It has an electron.
How many electrons?
One.
One. Okay, so one of the charges has to be the charge on a electron. Okay, so there's one charge. So there's Q, call it Q2, I don't care. Q2 is the charge on an electron. So Q1 would be, according to that expression, it must be what? All right, what does Q1 have to be? You're getting there. Well, what's the rest of it? Another E. Has to equal ZE squared. Has to be ZE. Now, what the heck was ZE? What the heck is Z? Now, E is the charge on a...
What's the atomic number?
Z is the atomic number. E is the... What's E represent again?
Electron? Well, energy? No.
What do we call Q?
Charge.
Charge. So E must be
Of an electron.
on an electron, charge of an electron, right? That you can look up in the inside front cover. So Q1, charge on an electron. So you have two particles, hydrogenic atom. One's an electron. So there's your Q1. charge on an electron. The other particle, Q2, must be Ze. What is this representing? The charge on the, it's hydrogenic. What's left?
The rest of that?
Yeah, more specifically,
The protons?
what's Z? You said the atomic number.
Yeah.
So if I want to draw any hydrogenic atom, I don't know, let's say magnesium, I don't care, magnesium. I want to make it hydrogenic. Well, that magnesium is not hydrogenic. What ion do I have to write?
Minus. G
G minus?
Plus 2?
And G plus 2? How many electrons do I have still?
10?
I have 10, so that's not hydrogenic.
Plus 12.
Plus 12. Now I have how many electrons? 0. That's not hydrogenic.
Plus 11.
Plus.
1.
Hydrogenic,
Count down.
magnesium plus,
1.
how many electrons do you have now? How many electrons do you have? Just do the math.
5 plus 11.
Plus 11.
Don't laugh at me.
All right? Plus magnesium plus 11 would be hydrogenic. So you have what's present? What is present here? 1 electron. Okay, that's your Q1. What's left? 12 protons. So your Z would be 12. So they want to know what the charge is on those 12 protons. All you do is just take the charge times the number that you have. Okay, plus 12. Because you removed that much. Okay? So that's all they're saying, is to get these hydrogenic atoms, right? You have the charge of 2 particles. One's always 1 electron because they're hydrogenic. And then the other one is the remaining charge, right? Z times an electron. So if you keep looking at that book on page 345, and you take a look at equation, so this is equation 5. And then if you go 1 down, equation 6, okay, they have their Hamiltonian written. And they really they blew it all up. They blew it up into the electron component and the nucleus component and the potential energy, right? So it's really pretty ugly.
And they have a little hat.
Yeah. They all have the little hats, right? Yeah, the H should have, the H is missing a hat. I don't know why they don't have it there. Good point. Okay, so you solve the Schrödinger equation. You keep going or flipping over here. And where are we here? Where's the solution? There it is. On page 348. Okay, page 348, that equation 13. There's our solutions. Right? That the energy is going to be Z squared mu e to the 4th 32 pi squared epsilon, the permittivity of free space, right? Look at all that stuff. Page 348, equation 13 is the solution. So you solve it.
That's a real equation we use, right?
Page 348, equation 13. So thank goodness we didn't have to do that. Okay. So what's the mu again? In that expression for the energy was a mu. What's mu?
Mass.
What mass? Reduced mass, right? Okay. What's N?
Quantum number.
Quantum number, right? So in these hydrogenic atoms, does little l and m sub l affect the energy? Look at the equation. I don't know if you have the equation. It's just a subscript. It's E sub n equals this big ugly mess. The only quantum number that matters, determines the energy is n. They didn't write little n, l, m sub l. No, it's just n. So with heterogenic atoms, you just have these shells, and everything is degenerate. Okay.
What does it mean by degenerate?
Oh, I would say this. This is great for degenerate. This diagram right here. Because if you pick an N, right? So here's all the P, the D's, and the F's, and they just keep going. If you pick an N, you have, here's 1s, for example. 1s is way on the bottom. Do you have any L's or M sub L if you're in 1s? No, right? Because the little n's only 1. It's not possible. So then you jump up to 2s. But now with 2s, you can also write 2, what's this one? 2p. Now there aren't any d's because the n's only 2. But notice how they're on exactly the same energy level. So all that matters is the n. L and M sub L, they're all in the same energy. So when you do get these high n's, where you do have s, where you have all three, you have p's, d's, and f's, look at that, they're all at the same energy level as the s. Okay. They're degenerate. The only thing that matters is the principal quantum number, n. But it comes to play if you want to know about transitions, then the principal quantum number doesn't even come into play. All that matters is conservation of angular momentum.
So degenerate means pretty much it's the same energy.
Degenerate means same energy.
Okay.
Yeah, that's all degenerate means. Same energy. Same energy. Okay. So, hopefully I didn't confuse you more. Let's see. So now we're doing everything below the line. Okay. And, good. We're not done. We don't have to write an exam. Okay. So we're on 5. Now remember, do the hints here. Like on 5, we're only supposed to do part A and see equation 6, page 345. Okay. And then 7 has its own hint too. Okay. Oh, good. Whoever typed these up for me retyped the hints. That was nice. Okay, number 5. Calculate the average kinetic and potential energies of a 2s electron in the ground state of a hydrogen atom. Okay. See equation 6, page 345. And use your size.
Big old nasty.
It's big old nasty. Oh, we're only doing average potential energy. Man, I should have you. Look at this. This is the work to get the average kinetic energy. Man, that'd be a good one for you guys to do. We'll keep it the way the notes say, but that would take you a while. So let's not put you through that. Let's stick to the average potential energy, right? Okay, so let's use their hints. So we're not doing kinetic. Okay. See equation 6, page 345. What the heck am I talking about here?
You learned on the way.
Okay. Oh, that's what I was talking about. Okay, so when they want the average anything, we're supposed to calculate, what do we call these? Expectation values, right? So the idea is you do this, and then the expression looks like what? Psi star times the operator times psi d tau. Okay? Excellent. See, he doesn't even show up, and he knows this stuff. Okay. Now, what is our operator? Our operator is, what do you want to find the average of? Potential energy. And we said that was a V. So if we want to follow our notes appropriately, we should put a little hat on it. Okay? So don't get confused. I mean, whether the book has a hat on it or not. Oh, they did. Nice, they did. So if you go back to equation 5, where it says the hint, I lost it. Where it says the hint, equation, there it is. Equation 6, page 345. So that's what I was pointing at before. If you look at that and you compare, see, equation 6 has H equals this whole big mess, and then right below it equals a whole another big mess, right? But in the top one it has plus V hat plus, that's what V hat is. Right? That's where I'm getting this from. Right? That the book says, here's the Hamiltonian operator we're going to use. This is what I was talking about before, that they solved and got all of our energies.
Yeah.
Okay, if you don't have your book, this is the same Hamiltonian operator it's talking about. So this V hat, well, what is it? Well, the next expression down, they actually gave it to you. So that's what we need to calculate. That's what we need to put inside here.
Oh, that's like a Z.
All right, so we're going to calculate and just put that in exactly. It's negative ZE squared. All right, or 4 pi E naught R. So that's where that's why we're starting that way.
What is that 4 pi 2r?
Now,
No, it's the E naught. It's like
so again, you watch where this stuff is coming from. Whether you can read this or not, you got to see where it's coming from so you can reproduce it. Where is this coming from? It's coming from equation 6, page 345. And how did I get it? Because here it is right here, V hat. And that's what we want. But what is it? Well, you got to look down to the next equation, and they tell you exactly what it is. And that's where I'm getting this from. So it's kind of good if you can't really read my writing, because I want you to see where I got it from.
that's cool.
Okay? So I want you to kind of see where I got it from. I'm getting it from right here. Right? In fact, just leave it blank so you can see this. All right, that's probably better. Okay? Now we have to do psi star psi. Right? Here's our wave function. Now, how do we get the radial and the spherical component?
Oh, so
Do we memorize these?
radio and spherical.
Yeah, spherical harmonics and radial wave functions
Let me check my cheat.
from, it says right there,
Tables
12.3 and 13.1. So we're going to need that stuff. Tables 12.3. Now, that it might be on the cheat sheet. They don't have to go looking for these. Do we have an equation sheet for this chapter?
No,
We don't have an equation sheet? Shoot, I didn't include one. Well, we're going to have to look them up then. Table 12.3. Okay, table 12.3 is on page 334. .334. So, and we are supposed to use, now that table has a bunch of L's, M sub L's, and, right? So which one are we supposed to be looking up? Because in that table, that's where we'll get our Y. It's a little L, M sub L. Which L and M sub L did we pick?
would be the one that says 0, 0.
Why?
Because it says hydrogen atom.
Well, hydrogen atom can have a lot of different states.
Oh, no, it's not. It's a 2S.
2s. Okay, that's what you go by. So what is your L and M sub L? if it's 2s?
It would be, it'll be 1 0.
It says in the question.
It should be 1 0, right?
So you're saying,
I will be 1 and M sub L will be 0.
does everybody agree? If you're in the 2s, no, what is,
I'm disagreeing.
if L is 1, what did that mean? What hydrogenic orbital do you have?
Oh, S. So.
L is 1, was it S?
No,
Go
S
back
is-
to your
S-
concept
S-
preview.
S is 1, and then P was 2, D was 3. No.
S is 0. P is
S
1.
is 0.
P is 1, yeah.
Okay,
I'm right.
so little l has to be what? If you're in the 2s,
It's gotta be 0.
little l has to be 0. What does little m sub l have to be? 0. Is that its only choice? Yeah. Right? Because it's an S. Concept preview. Okay. So we have to look up the one for Y00. And on page 334, table 12.3, that's just 1 over 4 pi square root. Thank goodness, right? It's not some big ugly thing. Okay. Now we have to look up the radial component. And find, let's see, what page is that on? Maybe I have it marked. Yeah, I do. Page 349. That's on page 349. The radial component. That's on page 349. Okay, and the radial component has subscripts of N and L. So we have to look up R what? What are the subscripts? Yeah, so what would you put in there for those two?
Would be 1 0.
Remember, 1 0? What's the electron we're interested in?
2s.
2s is a 2s electron.
So it means
1 0,
L is 0.
L is 0.
Yeah,
That
and
means
N,
there's N would also.
no, N would be 1.
And is 2.
N is,
No, because it's
yeah, you guys, we need to review.
Because it's N minus 1. So P is 1, so 1 minus 1.
Let's practice some of these.
No. It's got to be 0 because if your L is.
Oh, let's you guys are, jeez, you don't remember this. All right, this should have been, we should have had a quiz on this. 3D. Every electron has to have a set of quantum numbers. N, L, M sub L, right? All right, so list them out. You could have 3D. Let's make a nicer table. You could have 3D. You could have 2p. You could have 4f, right? If you have a 3D, an electron in a 3D orbital, what's my N?
2, 3. Because S is 0. F.
This is always your shell. The number out front is always your shell, right? Look what we did up here, right? We call this 1s, right? Because n goes, what's the lowest n can be? 1. So that means, right? So that's why it's 1s. And that's the lowest energy. N can be 1. Then you have the shell where n is 2, and on. So if you have,
What's the other thing called where it's like you. Okay, I guess that would be your L.
okay, what is L if you have a 3D?
Would that be 2?
You agree? Everybody agree? It has to be
2. Oh, yeah.
has to be 2. Then your M sub L,
-2.
yeah, there, now you got a choice of them, -2 all the way to +2.
Remember that one.
How about 2p?
It's not be 2 for your N.
N has to be 2, L has to be 1, M sub L, -1 all the way to +1. 4f,
4. And 3 for your L.
yeah.
Maybe that makes sense now.
Okay, back up. We have to write, remember this is our question. You've got this ugly table back up. Where do we go? Here it is. Here's our wave function that we have to write and we have to put in right here, right? Well, we have to write it. So we got the spherical, the angular. Now we need the radial component. And according to that table on page 349, the radial component looks like RNL. So what numbers do we need there? What subscripts? Everybody agree? 2 for the n?
Yeah.
2 for the n.
We just did it, right? So it'd be 1.
0 for the
Zero.
L. Yeah, 0 for the L.
If you say 1,
Then that means.
if you say 1 for the L, you just said that was
Oh, that was
P.
that.
Right, so it has to be
Zero.
0 because it's what an electron in what orbital?
That's
2 2s. 2s. All right? Okay. So we have to look up R20 in that table. So you go to page 349.
So a 2s and a 2p have the exact same n, l, and ml numbers?
2s and a 2p.
2s and a 2p will have
No.
the exact same.
2p, the n will be 2, but the l will be 1.
Well, let's add 2s to our table. All right, you add 2s. N's going to be 2.
L, 1.
No, it'll be
1.
It'll be 0 for that
Zero.
one.
Because that's when that comes in, right? The S.
All right. Remember, if L, what are the possible values for L?
Negative 1. Positive, negative L. 2.
0,
1, 2, 3,
all the way up to
4, 5.
n minus 1.
Oh,
Okay, so what can, if it's 0, what's the little letter?
okay. S.
S. If it's 1, P. 2, D. Right? Keep going. All righty. So we need to write R20. We're losing everything here. A lot more space. So our wave function will be,
Okay, now let's make one more question for you. How'd you know you needed the radial and the orbital?
right here. It's in the question. It's in my hint that I'm being so nice to help you with.
Well, as I'm saying, how would you know if you didn't give us the hint?
Well, you better don't expect too many hints on an exam, right? You're gonna have to know it without all these little hints. So how do you write the wave function? All right. Radial component, angular component. So we already found. We look up the R. We said that was 1, 0, right? I want to go make my mistake. 2, 0. R20. Oh, now we have something ugly to write down. Ugh. All right. Well, I should probably write it in here.
And the R, that's all radial?
Mm-hmm.
Okay. I see it's there.
Okay. Well, let's not jump. Okay, let's not jump. I don't want to lose you. Whoa, what was that? What the hell? Okay. Our radial component. I'm just copying this right from the table. And what's my Z?
Atomic number?
Yeah. Because instead of writing Z here, at least I can substitute in what Z is. According to this question, what's Z?
One.
Yeah, 1, because it's a what atom?
Hydrogen.
Hydrogen. So Z will be 1. So I've got 1 over A naught to 3/2. I'm not memorizing this stuff. I'm just copying it down from the table. Okay. So there's my radial component. And then my angular component we said was 1 over 4 pi square root. Okay, so now you have pretty much everything you need. Right? So we'll put in your expression. All right. Expectation value. V hat. Integral. Right? Psi star. So we're going to put this whole thing. Oh, what we should have done, instead of writing these rows, because what are we integrating over?
Writing over rho equals.
What's our variable? Is our variable rho? What we're integrating? Our variable? What are we integrating? All right. So remember we talked about what rho was? You have to look in the really small print.
Yeah. It'd be 2ZR.
2ZR over A naught is the bottom of that. So we should probably, wherever we see a rho, we should write 2ZR over A naught. That might, then we have to rewrite this whole big thing. 2ZR over A naught. All right, because my Z is 1. E to the negative rho over 4. Two ZR over A naught over 4. All right? Okay. I'm on track here. Okay. All right, so now we just gotta, so here's our, we'll put it in here. You put in your operator, which we said was,
Negative Z A squared over 4 pi.
but Z is 1 though, right?
Yeah.
So we said it was, where did I write it down?
You never wrote it down. You just said so second page.
Oh yeah, okay. So this is where you put in that expression for the V hat, right? Then we have to write the wave function again, and then what do we write?
D tau.
D tau. But instead of writing D tau, you could substitute in,
R squared, dr, sine theta.
yeah, there it is. So really, this is the triple integral.
Yeah.
All right. So you have a theta part, a phi, and R.
So when we read this question, it says calculate the average kinetic and potential energies of an electron in the ground state. We're supposed to know that. We're supposed to look up the radio and this.
Yeah, because this is the only way. Because for a 2s electron, right? That's what I was kind of running it through you on page. It all started there on page 345 in the book, right here. Yeah, right here when they're trying to solve the Schrödinger equation and get all their answers and get this to explain all the different lines and describe all the states. Well, you had to write a wave function. And how do you write the wave function? What they did is they said, hey, we have to write our wave function this way. A radial component times y. And we look those up in those tables. That's how we're going to write our wave function. And then we go ahead and solve it. Solve the Schrödinger equation.
How about if they didn't give us 2s electron?
Then all they would do is just give you something else. The electron has to be in one of those orbitals.
How about if they give you nothing? They don't see 2s electron or anything at all. Well, 13.5 doesn't say anything of that sort. It says calculate the average kinetic and potential energies of an electron in the ground state. What's this ground state?
Well, ground state would be 1s. So I'm changing the question then, I guess.
Okay.
maybe she. Oh, she typed it up wrong,
Well,
didn't she?
The problem you're doing is 13.5B.
Oh, I'm doing 13.5B.
Yeah, standard.
All right. Yeah, I see what you're saying. What page is this on that you're looking at?
383.
Page 383. So page 383, if you're going to do the homework's asking you to do number 5. I didn't ask you to do 5B. Right? Oh man, I'm setting you up to do a B exercise. I thought it said oh yeah, when she typed it up, I was praising whoever typed it up. We did 13.5B. But what would change? It should be a little bit easier. What would change?
The radial equation we use.
Yeah, the radial equation will be simpler. Because it'll be which radial equation would you pick for 1s?
What would be a circle?
It'd be r with little subscript 1 and 0. So that's the r that you would use if you change this to 1s.
So the equation, the question's typed wrong?
Yeah, it's typed up for B. That's fine. We can do B. You can do B. I'd take either one in the homework. B's more work. Because it's an uglier wave function, I think. Maybe not. But yeah, 1s would be a lot easier.
Well, not only that, we can check our answer if it's right.
Yeah.
1B, like we do it, and we get an answer like, oh, it's right.
Yeah.
We don't know if it's right.
Yeah.
I'm assuming it's right.
Yeah, so there's an advantage there's an advantage of this. So this is set up all for 2s, right?
Yeah.
The homework asks for 1s. So if you go through and start at the beginning and set this up for 1s, your reward will be that it's going to be an easier problem. Or you finish this for 2s, it's already set up for you, but the math is going to be uglier, right? So you have two options there. I'll accept either one.
I like the one that has a reward.
I would take the one with the reward too. Looking at the math, you should do the one with the reward. Okay. So you have a good shot at setting that up.
Something beat on. Was I zoning out that whole time?
How about 7?
Is that one type right?
Nah, I should probably take a look. I think it is. Now, how did we calculate? We called these projections, and we actually calculated what this question is asking in number 7. Now, they just didn't use the M word. They didn't use magnitude. But it's true. What is the orbital angular momentum? I mean, that's magnitude. What is the speed of something? No one ever says magnitude. They just say, what is the speed? So the English is okay. It's just technically we're calculating magnitude. But what is the orbital angular momentum of an electron? How do we do that in these projections? Remember the projections? How do we do that? The length of the arrow in that projection. Right? Good. Yeah, in general, you're there. But in general, it was the square root times what? H bar. That's how we calculated magnitude of angular momenta. And they use J because there's a couple different types of angular momenta. There was spin, intrinsic spin, and there was orbital angular momentum. So that's why they just wrote it in general. But pretty much, you just got to figure out what your little L is going to be, because they want angular momentum. Figure out what your little L is going to be, put it in here, and you're done. Right? And they want the number of angular and radial nodes. And the hint is the total number of nodes is n minus 1. And I think we talked about it earlier. The number of angular nodes is actually just little l.
Oh, thank God.
All right? Okay.
Yesterday's homework was just killer.
And number 10, make sure this one is typed up right. I think it is.
This is not to be turned in.
10's not to be turned in?
Because you put B.
What are you talking about? Yeah, B exercises.
Yeah, but having for exercise.
Yeah, there's,
Tens of B exercise.
but there's, yeah, but it's not after the one that says don't turn them in.
Oh yeah, it says B exercises 10. B exercises not to be turned.
Yeah. So would you turn in 10?
No.
So no.
What's this B exercise?
I choose to read the other.
You can choose to read whatever you want. If it says B exercises, turn it in. You better bloody well turn it in.
Yeah, I'll turn in 10B. Okay,
What
fine.
what says not to be turned in though?
I'll negotiate.
Yeah. So what is
Not to be turned in.
what is after? What's not to be turned in? Semicolon. What does it say? Which problems? Nothing. So is it saying anything at all? It's just something that was copy pasted. There's nothing. There's no information there. If I say don't do exactly this, and don't tell you anything.
So like
What? That means you do nothing ever in your life? You guys are really looking for ways to get out of work here, I think.
Pretty much.
10
it's
is,
off week, man.
10 is really hard. 10 is super easy, so I don't think it'll be easy.
Yeah. State the orbital degeneracy. So you got, what's the trick to doing that one? What was the, we did this in the concept preview. What was the, we counted up all these different orbitals. The degeneracy was always what? N squared. That's all it is. Figure out what n is.
I thought we did this one already.
So figure out what the n is, and you got your answer.
Well, at least I did.
Okay. Figure out what the n is.
So
Get your answer.
Yes, right, we are turning 10.
So-
Yes, problem solved.
So what equation are you looking? Where's this RH coming from?
that's a rolling.
Right? Look for it. It's got to be an expression for energy with a Rydberg constant. There's one of them. Here's one of them, but I don't think this is really going to help you. Right? Here it is. Right? So to me, the big hint was seeing that capital R. Because then, if they give you an expression, you can figure out what n squared is. Okay. So we're about out of time. So give it a shot, and I'll be glad to help you out.